Imagine waking up tomorrow and discovering that satellites in low Earth orbit can no longer maneuver.
No che ličene voidens.
No last-second course corrections. No way to move out of the path of another spacecraft. How long would Earth have before something goes wrong? According to a new research metric called the crash clock, the answer is shockingly short. As of May 2026, the estimated timescale is just 2.5 days. But there's an important catch. That does not mean a satellite collision is scheduled to happen in 2.5 days. The clock measures a hypothetical scenario. What happens if satellites suddenly lose the ability to maneuver? And compared with 2018, when the same metric was measured at 164 days, the safety margin has collapsed. So why is Earth's orbit getting this crowded? How often are satellites actually dodging each other? And what happens if one day they can't? Let's get into it. From the ground, space looks infinite. Black sky. A few stars. Maybe a satellite crossing overhead. But hundreds of miles above Earth, the situation is very different. Low Earth orbit, or LEO, has become one of the busiest pieces of real estate humanity has ever created. And the biggest reason is the rise of megaconstellations. Instead of launching one enormous communication satellite, companies can launch thousands of smaller spacecraft into carefully designed orbital shells. The best-known example is SpaceX's Starlink network. Starlink satellites operate primarily in low Earth orbit, with large numbers occupying relatively concentrated orbital shells. And this creates a very different orbital environment from the one that existed just a decade ago. The problem isn't simply the number of satellites. It's the density. Thousands of spacecraft are moving around Earth at orbital velocity, crossing different paths, sharing limited altitude bands, and constantly changing position. That means satellite operators increasingly have to know not just where their own spacecraft are, but where thousands of other objects are too. Here's the part that sounds terrifying until you understand what's actually happening. Satellites are already performing collision avoidance maneuvers all the time. And that's a sign the system is working. SpaceX reported more than 355,000 collision avoidance maneuvers involving Starlink satellites between June 2025 and May 2026. That's an enormous number compared with the early years of satellite operations. These aren't 355,000 confirmed near crashes. They're automated responses to predicted conjunctions. Situations where another object is expected to pass close enough to create a potential collision risk. Starlink uses autonomous systems to evaluate these encounters and, when necessary, adjust a satellite's trajectory. Sometimes the spacecraft moves. Sometimes the other object moves. Sometimes updated tracking data shows that no maneuver is actually necessary. So the huge maneuver count shouldn't be interpreted as hundreds of thousands of collisions almost happened. It tells us something different. The orbital environment now requires constant coordination. And that dependence is exactly what the crash clock is trying to measure. The name sounds like something from a disaster movie. But the crash clock is actually a scientific risk indicator. It stands for collision realization and significant harm. The basic question is simple. If satellite operators suddenly lost the ability to perform collision avoidance maneuvers, how long would it take before a potentially catastrophic collision occurred among tracked objects in low Earth orbit? Researchers developed the metric to quantify how dependent modern orbital operations have become on continuous maneuvering and situational awareness. And the historical comparison is striking. In January 2018, the crash clock was about 164 days. By June 2025, the updated research gave a value of 5.5 days. And by May 2026, the latest published value had fallen to approximately 2.5 days. That's an enormous change. But remember what the number means. It isn't saying Earth will have a satellite collision in 2.5 days. It's saying that if normal collision avoidance operations suddenly stopped, the statistical timescale for a potentially serious collision would be extremely short. That's a measure of how little recovery time the system may have after a widespread loss of control. The biggest reason is simple. There are far more objects in orbit than there used to be. Megaconstellations have transformed low Earth orbit from a relatively sparse environment into a highly populated one. And as the population grows, the number of possible close encounters grows as well. There's another important factor. Satellites don't just move in one giant circular highway. They're distributed across different altitudes, inclinations, orbital planes, and shells. Two objects can therefore have very different orbits while still coming close enough to create a conjunction. The research behind the crash clock found that close encounters have become dramatically more frequent in the most populated regions of LEO. In simulations, encounters within 1 kilometer became far more frequent between the 2018 and 2025 orbital populations. So the issue isn't that satellites are randomly crashing into one another. It's that the number of opportunities for something to go wrong is increasing. Now comes the frightening question. What could actually cause large numbers of satellites to lose the ability to maneuver? One possibility is a major space weather event. A powerful solar storm can interfere with communications, navigation, electronics, and the upper atmosphere. It can also increase atmospheric density at low altitudes, changing the drag experienced by spacecraft and making orbital predictions more complicated. And if a widespread event seriously degraded satellite communications or situational awareness, operators could temporarily lose the ability to coordinate avoidance maneuvers. The crash clock research specifically uses a severe disruption, such as a major solar storm, as an example of the kind of event that could test this shrinking safety margin. But solar storms aren't the only possibility. A major software failure, a widespread communications outage, a serious cybersecurity incident, or another event that prevents operators from controlling spacecraft could create similar problems. The point isn't that one of these disasters is about to happen. The point is that the system has become increasingly dependent on continuous operation. And then there's the problem that doesn't need to be controlled by anyone. Space debris. A dead satellite doesn't simply disappear. A spent rocket stage doesn't necessarily fall back to Earth immediately. And fragments from previous collisions can remain in orbit for years, decades, or even longer. Now imagine two satellites collide at orbital velocity. The spacecraft don't simply bounce apart. They can fragment into a cloud of debris. Each fragment becomes another object that can potentially hit another spacecraft. And that brings us to the phrase everyone has heard. Kessler syndrome. The concept, proposed by NASA scientist Donald Kessler and colleagues in the late 1970s, describes a situation where collisions generate enough debris to increase the likelihood of additional collisions. One collision creates debris. That debris creates more collisions. Those collisions create more debris. And the process can feed itself. But there's an important distinction. A catastrophic Kessler syndrome scenario isn't an inevitable consequence of today's satellite population. It's a potential long-term runaway scenario. Researchers are concerned because certain highly populated orbital regions can have much higher collision risk than others, but that doesn't mean the entire planet's orbit is about to become unusable. Here's the good news. We aren't blind. Ground-based radars and telescopes constantly track objects in Earth orbit. Satellite operators receive warnings about potential close approaches. And modern spacecraft can automatically perform avoidance maneuvers when necessary. SpaceX, for example, has been lowering the operating altitude of Starlink satellites as part of its constellation design. Its current plan calls for Starlink satellites to be lowered below 500 kilometers, reducing the time they would naturally take to re-enter if they become inactive. Other organizations are working on debris mitigation, improved tracking, better coordination, and eventually active debris removal. Missions designed to physically remove large pieces of dangerous debris from orbit. None of these solutions is perfect. But the most important thing is that the problem is now being measured. And what gets measured can be managed. So, is a catastrophic satellite collision inevitable? No. And that's important. The crash clock isn't a doomsday countdown. It's a warning. In 2018, the hypothetical no-maneuver collision timescale was measured in months. By 2026, the latest value is measured in days. That doesn't mean satellites are about to crash. It means our modern orbital infrastructure has less room for a major failure than it once did. Every day, satellites communicate. They calculate. They track. They maneuver. And thousands of spacecraft quietly share the same orbital environment without colliding. For now, the system works. But as more satellites go up, the question becomes increasingly important. How much complexity can Earth's orbit handle before our safety systems are pushed too far? Because the most dangerous thing in space may not be what's coming toward Earth. It may be what's already circling above us. If you want to keep exploring the hidden risks and breakthroughs shaping humanity's future in space, subscribe to Deep Space Files. Because sometimes the biggest space stories aren't explosions. They're the disasters we are working every day to prevent that is happening right above your head.